This video lesson. In this video, we are going to look at some practice questions on the 5 equations of motion which are derived for uniform acceleration, focusing on problems in vertical direction. Note that the first 4 questions in this video are taken from physicsclassroom.com, and let's just get right into it. We got a kangaroo, which is capable of jumping to a height of 2.62 meters, and we want to determine the takeoff velocity of the kangaroo. Here's how we're going to start off this question. We're going to start off with our diagrams. So stage 1 is to draw it out. This is a vertical motion because the kangaroo is jumping. So I'm going to draw the kangaroo as a box. And the kangaroo is going to have some sort of initial velocity. I'm going to represent that like this. And this is at stage 1. So it's going to be velocity 1. And its magnitude, we don't know. So I'm just going to put a question mark. The kangaroo is going to displace for a certain amount, and then at some point it's going to reach this location. And at this point, it's going to have some sort of velocity. I'm just going to say velocity 2. And this is the displacement from 1 to 2. Good. And it's going to take the kangaroo a certain amount of time to get there as well. And there's going to be acceleration acting on the kangaroo, and the acceleration is going to be pointing down. The only force acting on the kangaroo is the force of gravity or gravitational force. And that is going to have a magnitude of 9.81. I'm going to take up to be positive in this example, and I am going to use units of meters and seconds. So my fundamental units, so any value that I put, acceleration would be 9.8 meters per second squared. What other information do I have? I know that the height is 2.62 meters, so that would mean the displacement of the kangaroo is 2.62 meters. And again, I do like to highlight my conventions there. Good. And is there any other information that I have? So we know that the kangaroo is capable of going this height, and we want the takeoff velocity, so we want that initial velocity there. And that's it. That's all we know. So basically, we have to figure out if we can figure out any other information. Does the question imply anything else? So we don't know anything about the time, and that's okay. The velocity 2, when the kangaroo jumps, when the kangaroo is at its peak, its velocity is going to be 0, and that's implied basically based on the question there. So that's 0 meters per second. And now I have 3 pieces of information. I have the displacement, velocity, and acceleration, and based on that I can find the 2 other pieces of information. Next step is to do my physics representation, and I am going to do that with a few graphs. I'm going to have a position time, I'm going to have a velocity time, and I'm going to have an acceleration time. Okay, so my position time, so in my position, I'm taking everything to be up, even acceleration, I'm taking it to be up in terms of my graphs. So my position, let's do velocity first. So we're going to start with some sort of velocity. It's going to be a positive value because it's going in that direction, and my positive is also in that direction. So we're going to start off, let's use a different color here, use dark blue. I'm going to start off at a velocity, and this is stage 1, and when I reach stage 2, which is right here, we're going to be at 0 velocity. So I'm going to put that stage 2, and we're going to make an assumption that this is constant acceleration. The acceleration is going to be negative, or in the downward direction is constant because the slope of the tangent of this line is constant, and it's a negative value. And then we get the position, we need the position time graph here. So we're going to assume that the reference point is right here. Starting at position 1, the velocity is high value, and we will get a slope in this direction. And at the very end, its position is going to be in the positive direction as compared to the reference point, and therefore it's going to be landing somewhere here. So I'm just going to put that here. Stage 2, this is stage 1. And at this point, the velocity is 0, and that means the slope of this line should also be 0. So I'm going to put a dashed line like that for the tangent, and I'm just going to connect them. So this is going to look something like this. And this is good. It shows that the velocity initially is upwards. It's got some sort of magnitude. It slows down as the acceleration is slowing it down, and it reaches a velocity of 0 at the top there. So let's move on to part C, which is our assumptions here. And for the assumptions, we are assuming that the acceleration is constant throughout, and that's because the height that it's traveling is not that much, and therefore the altitude isn't changing much. We are going to make an assumption that there's no air resistance or wind effects here. So I'm just going to include them all together, and that's it. That's good. So when there's no air resistance, that means the object is not hitting any air particles as it's going down. So it's not so that's not causing an extra acceleration on top of the gravitational acceleration. Now, stage D is going to be our mathematical representation. So we are asked to find the takeoff velocity. So we have the acceleration, the final velocity, we need to find the initial velocity, and we have the displacement. What we don't have is time, so we're going to look for an equation that doesn't have time in it. This one has time, this one doesn't have time. That's the one we're going to use. I'm going to use a little arrow here showing which one we're using. And let's get on with it. So this is final velocity is equal to, so our final event here is event 2, so that's final velocity squared is equal to the initial velocity. For us, that's 1, plus 2 times the acceleration. This is the acceleration from 1 to 2. That's pretty constant at 9.81. And our displacement from 1 to 2. We're going to plug in the values. So velocity 2 in this case is 0 squared is equal to, our velocity 1 is what we're trying to find. You can notice that it's in the same direction as our positive, so we're going to just use a positive v1 here. We're going to add 2 times the acceleration. For our acceleration, our positive is upwards, but this is acting downwards, so we have to use an opposite sign. So in this case, we will use negative 9.81. And our displacement here is going upwards. That's same as my positive convention. So the displacement from 1 to 2 is I have to put a positive value in there. So that's 2.62. Let's do the calculation. We got 0 is equal to v1 squared minus 51.4044. I'm going to add 51.4044 to both sides. I'm going to take the square root and I will get 7.1696, and then it continues on. But basically, based on my question, I have 3 significant figures for my change in position, and I have 3 significant figures for my acceleration based on 9.81. And our final velocity is 0. We're assuming that has infinite number of significant figures because it stops. And my final answer is only good to 3 significant figures then, so I will estimate my answer as, or round it to 7.17. My unit is meters per second, and my direction is going to be in the positive direction there, so that's up. And I can just put an arrow there. I'm gonna box my final answer, and this is the initial velocity. And it does say velocity, so we do need to include the direction. If it had just asked for speed, we could avoid the direction there. In terms of evaluation, I'll just talk about it. So we're going to make some questions about what will happen if we had air resistance, for example, or acceleration wasn't constant. So if if there was air resistance as the object was going up, it would slow down even further because of that extra air resistance. So in order for it to travel the same amount of distance, then this velocity should increase to kind of be able to travel as far, because it's being pushed back by the gravitational acceleration right now, and it would be pushed back further by air resistance if there was air resistance. So that velocity would need to increase in order to kind of get the same displacement. And if the acceleration wasn't constant, so usually as the altitude increases, gravitational acceleration actually decreases. So if that's the case, if the gravitational acceleration is decreasing, that would mean it's going to be easier for the object to travel further, so a little bit less velocity here would be able to handle that. So those are kind of some of the stuff we can talk about in terms of evaluation, or some of the questions I may ask you. I might ask you what happens if the height was longer and gravitational acceleration was no longer constant, or what would have happened if there was no air resistance. Let us look at the next question. In our next question, we got a baseball which is popped straight up into the air and has a hang time of 6.25 seconds. And we want to determine the height to which the ball rises before it reaches its peak. Okay, so we want to figure out when it reaches its peak. And for those of us who don't know what hang time might mean, here is a hint which says the time to rise to the peak is 1/2 of the total hang time. So if a ball goes up and comes back, then the hang time is how long the ball has been in the air. And in this case, we're given a hint which says as the ball goes up, it's let's say it takes 10 seconds to get there, it's going to take 10 seconds for it to come back. So the time it takes for it to go from the ground all the way up is going to be half of this, and that's going to be helpful. Let's draw out our situation. We got a baseball which starts, let's say, at this position. This is our position 1, and it's going to go up. And it's going to reach somewhere here. And I'm going to label this as stage 2. And what are the information that we can take from this? So initial velocity. And I'm going to draw this even a little bit bigger. Final velocity. There's going to be a displacement from here to here. So I'm going to draw that as displacement from 1 to 2. And I'm actually going to erase the arrow here because the arrow is already included as a vector there. And I'm just writing the magnitudes here. And there's going to be a time it takes for this to happen, and there's going to be an acceleration acting downwards, and that acceleration is equal to 9.81. I'm going to take up to be positive for my sign convention, and I'm going to be using the fundamental units here. So let's highlight all of that so it's nice and clear. And let's put any information that we know. What we want to see what is the total height, and in order to figure out what is the total height of the object when it raises, then we need to figure out when it stops. And in this case, velocity 2, or the speed at that point, is going to be 0. Initial velocity is not given to us, so I'm going to put a question mark there. We have the acceleration, which is nice. We don't have the displacement, so that's what we're trying to find. So I'm going to put a question mark there. For the hang times, or sorry, for our total time, we know that it's half of 6.25. So I'm just going to put 6.25 divided by 2. And that's going to equal to 3.125. Note that I'm not rounding my value to 3 significant figures yet. I will only round my very, very final answer here, and not anything that I do intermediate in my intermediate steps. I believe I have all the information that I need for this question. I'm going to go to stage 2 and draw my graphs here. So I'm going to have my position time, velocity time, and acceleration time. So position, velocity, and acceleration, and time, and time, and time. And this is stage A, and this is stage B. For my position time graph, I usually do that last, but let's just talk about initially. I'm going to take this to be my reference. So we start at the reference, and this is stage 1, and then stage 2, we're somewhere here. We're much further away from the reference point in the positive direction, because I'm taking up to be positive. I end up to the positive side of my reference point, and that's why I'm here. For velocity time graph, I start at a high velocity, positive, and I reach a speed of 0, so that's stage 1, that's stage 2. I'm going to connect them using a straight line, and therefore my acceleration is going to be negative throughout and a constant value. We know what that value is already. It's got a magnitude of 9.81, and you can see that it's opposite to my positive direction, so you can see the negative there. And for my position time graph, it's going to look very similar to the last question. We have a positive slope because we got a positive velocity here, and we got a 0 slope here because we got a 0 velocity down there. And then we connect the points, so it starts at a positive slope for the tangent. It's going to end with a 0 slope, and then connect it to curves using a nice curve, and that will end it there. Good. And that's my stage B. For the assumptions, so we're going to assume very similar to the last question. So we're going to assume that there's no air resistance or wind effects slowing it up or speeding it up, and we're assuming that there's constant acceleration. And to be more exact here, that the height is small enough that the gravitational acceleration doesn't actually change with altitude. Okay, and then once we're done this, we're going to do stage D, and I will write that here. And for stage D, first we need to figure out which equation to use. Let's highlight all the information we have. We have the total time it takes for this to happen. We have the acceleration, and we have the final velocity, and we're trying to figure out the height, or in this case, the displacement, which is this one. What we don't have is information about initial velocity, so I'm going to look at an equation that doesn't have initial velocity. This one does, this one has, this one doesn't, so that's what I'm going to use in this case. I'll write it down here so we have a little bit more space. Displacement from 1 to 2 is going to equal to my final velocity, which is velocity 2, multiplied by the change in time minus 1/2. And this change in time from 1 to 2, 1/2 of the acceleration from 1 to 2, multiplied by the change in time squared. Let's plug in all the information that we have. The displacement This is nice because it's already isolated for us. It's going to be equal to velocity 2 is 0. 0 times any number is 0, so that crosses this whole term out, and we get negative 1/2. My acceleration in this case is 9.81 in terms of magnitude. Its direction is acting downwards while my positive is upwards, so I have to use a negative value here. Negative 9.81, and the change in time, that doesn't have any directions, so that's going to just be 3.125. And I forgot a square there. I'm going to add that in. When I do this, I'm going to get 003 dot dot dot, and I have to see how many significant figures I have. So 9.81 has 3, 6.25 has 3, and 0 here is stopped, so we're going to assume infinite number of significant figures. So this needs to have the least, which is also 3, so I'm going to round this to 47.9 meters, and that's in the upward direction. That's consistent with my positive sign convention, and I'll write that as displacement from 1 to 2. And what is the question asking? The question is asking for the height. It's not asking for the displacement, so we'll just say that height is equal to, we don't need a direction for that one, that's 47.9 approximately meters, and that is my final answer. So I have to change this to 47.9 when we do it to 3 significant figures. Okay, I have my final answer here. That's part D. And for part E, in terms of evaluation, very similar to the last question. If you add air resistance, oh, actually, in this case, we're asking for displacement. So if we add air resistance, if we had the same initial velocity, then it's not going to go as high because the air resistance is going to act on top of the gravitational acceleration to slow down the ball. So it's not going to reach as high as it did last time, so the height would actually decrease. And if the acceleration isn't constant, so if you're throwing it up at a very, very high altitude, for example, and the acceleration here is decreasing, as the acceleration is decreasing, it's gonna have a high, it's not gonna resist the motion of the ball as much, and therefore it can reach a relatively higher height. So those are some of the things in terms of evaluation. Let's move on to the next question. In this question, we got the observation deck of a tall skyscraper. It's 370 meters above the street, and we want to determine the time required for a penny to free fall from the deck to the street below. Okay, let's talk about this. We got a situation. Let's say we got a tall buildings, and we got a penny. I'm gonna draw the penny as a little ball, and this is going to fall, and it's going to have, so it's, I believe it's being dropped, determined to free fall. So we're going to assume that it's being dropped in this case. The question isn't worded that well, and I'm going to say that the velocity here is 0, and this is stage 1. And it's going to reach stage 2 just before it hits the floor. I repeat, just before it reaches the floor, and not when it hits the floor and stops. So just the moments before it reaches that point, the ball is going to be here, and it's going to have a certain displacement and velocity. So for velocity 2, we don't have it, so I'm just going to put a question mark. I'm going to actually increase this in size a little bit. I'm going to draw an arrow from here to here. That's going to represent the displacement from stage 1 to 2. And I'm also going to talk about the time from stage 1 to 2 as well here. I'm going to just write the information down here. And we're going to assume that the object is accelerating downward at 9.81 meters per second squared. We have to take up or down to be positive. I often take my direction of positive, same as my displacement. It usually helps a little bit. So in this case, it's displacing downwards. So I'm going to take down to be positive. And my units are going to be fundamental units. And I'm going to highlight this lovely information. And in terms of the displacement, the object is falling. So let's take this to kind of be our reference point as well. This is kind of our reference point. The object is moving in the positive direction of the reference point because positive in this case is downwards. So it's gonna be a total of 370 meters. So I'll write that information down. The time we don't know, final velocity we don't know, but we have enough information here. We have three pieces. We got initial velocity, the acceleration, and we got the displacement. I'm going to put a question mark here. And let's do our graph. So this was stage A, which is the system diagram. In stage B, we're going to include our three graphs of motion. So this is going to be position, velocity, and acceleration. Let's start with position, just drawing the two dots. Initial position is right at the reference point, and since I'm taking down to be positive, everything down will be positive and everything up would be negative. And the final position is somewhere down, meaning somewhere in the positive region. So this is stage 1 and stage 2 is somewhere here. And let's put a dotted line so we can draw all the other information. For the velocity, we start at velocity of 0, and eventually we're going to have a velocity in the downward direction, and that's positive in the downward direction. So we're going to land somewhere here. That's stage 1, stage 2. We're going to connect that using a straight line because we're assuming it's constant acceleration. And that would mean that our acceleration in this case is positive because the slope of that line is also positive. Does it make sense? We're assuming that when we know that the acceleration is downwards, down this time is our positive direction. Since they match, it makes sense that this is in the positive direction. In terms of how the curve goes, whether it goes this way or this way, we're going to look at the velocity time graph. Velocity is 0 at stage 1. That means the slope here is 0. And velocity at the end is a positive value, meaning slope is like this. And I'm going to connect them here. Slope is positive, slope, and connect them using a nice curve. And it looks something like this. You can see that as time passes, the slope gets steeper and steeper, and that makes sense because the velocity is also increasing. Stage C of the question is the word representation. So we can describe the motion. In this case, we assume that you know how to describe the motion based on graphs, based on previous lessons. And we're just going to talk about our assumptions. One, that acceleration is constant, and one that there is no air resistance or wind effects. And good, now we have our set of assumptions here as well. So let's start solving our problem using our mathematical representation, which I will do here. We want to figure out how long it takes for this. The information that we do have are initial velocity, acceleration from 1 to 2, and the displacement from 1 to 2. And we want this one. What we don't have is the final velocity, so we're going to look at an equation that doesn't have that. It's got final velocity, this one, This one doesn't have a final velocity. We're going to move right into that one and say that the displacement is equal to the initial velocity multiplied by the change in time plus 1/2 of the acceleration times the change in time squared. Okay, we can plug in the values to find the time, the displacement. Okay, we're going to look at directions. Displacement is going downwards from stage 1 to 2. Down is my positive, so I have to use a positive value here. Again, since the direction for displacement from 1 to 2 is same as my positive sign convention, I will use positive. Velocity at stage 1 is 0. 0 times any number is 0, so that whole term cancels out. And I'm left with 1/2 times the acceleration. Acceleration, it's pointing downwards. That's same as my positive sign convention, so I am going to use a positive value of 9.81. It all has to do with the direction, with relative to our, or sorry, the direction relative to our positive sign convention. They match, so we use positive. If they don't match, we use negative. And then is the change in time. Change in time from 1 to 2, that's the only non-vector quantity, so I don't have to worry about direction. And that's going to be 300 and, sorry, that's going to be what I'm trying to find. So that's going to be the change in time squared. I'm going to rearrange for my change in time. And I'll do this in 2 steps for students who might have a hard time with the math, but if you're finding this easy, then you can just do it in 1 step. Delta time here is going to be plus or minus the square root of 2379.81. And if you do this properly on your calculator, and time cannot be negative, therefore the time will be equal to 8.6852, and then it will keep going. And then we have to look at the number of significant figures. In our question, this one is given in 2 significant figures. And that's all we have. The 0, we can assume infinite number of significant figure because it's the dropping value, which is just automatically 0. And 9.81 also has 3 significant figures, so the minimum is 2. So the change in time here should equal to 8.7 seconds approximately. So I'm going to box my answer there, and I will change the solution to 8.7. Note that the change in time, it's not a vector quantity, so we just need a unit here and no direction. And let's talk about the evaluation, especially taking away our assumptions. So if we're assuming that there's no air resistance, so if there was air resistance, then as this object is going down, it's going to be resisted by the air particles that are hitting the penny as it's going down, and it's going to slow it down a little bit. And if it slows it down, it takes it a little bit longer to reach. So instead of 8.7 seconds, in reality it could be approximately 8.8, 8.9, or even 9 seconds, or approximately that much effect. It's not going to be significant, but it's going to have a minimum effect on it. If the penny was a little bit lighter, or if it had a bigger surface area, then there would be more air particles hitting it, and therefore it would even take longer, so that 8.7 would change to even a longer value if that was the case. Now, if we make our assumption about acceleration and how in higher altitudes the acceleration isn't as high, so it might not be 9.81, it could be 9.79 or 9.80, then there's not going to be as much pull on it right at the beginning, but there will be about 9.81 here, so it might be slower based on that as well. So in general, both of these assumptions are making this reach the final destination faster than it would actually do. But in this case, well, the altitude 370 meters is starting to become a little bit more significant, so we might see some of it, but you might see this reducing to 9.79 or 7.8 or 7.5, but even then, it is not going to have a significant effect, so we won't see this going into 10 seconds or anything with that type of altitude. Let's move on to our next question, which is question number 4. And in this question, we got a stone that's being dropped into a deep well and is heard to hit the water after 3.47 seconds. Determine the depth of the well. Great question. Let's draw it out. We got a well, and I'm just going to draw this in a simple term. We're going to have, imagine this is one side of the well, this is the water at the very end, and we are going to drop something. In this case, it's the stone, and it's going to be here at stage 1, and it's going to reach stage 2 right here. And it's going to be displaced from here to here, so I'm going to actually draw that as my displacement from 1 to 2. It's going to take a certain amount of time for it to reach that stage, and it's going to have velocity 1 here, and it's going to have a velocity 2 here. Acceleration in this case, because it's being dropped in the, well, it's being dropped from the air, so it is going to have an acceleration going downwards, and I will represent that like this. And we're going to make an assumption that it's free falling, or that acceleration isn't changing on it, and so the value is going to be 9.81. We don't know the displacement, so I'm going to put a question mark. We do know the time, 3.41. We know that it's being dropped keyword, meaning that it's 0 speed at the beginning. So let's highlight that actually in the question too. Drop means velocity is equal to 0 initial, and velocity 2 we don't know, so I'm going to put a question mark. We already know 3 pieces of information. We can solve for the other 2 already. Before we do so, let's look at our graphs of motion in this case. So this is part B, and we're going to have position time, velocity time, and acceleration time. And I've already forgotten to do something. I'll do it in a second. And I have forgotten to draw my positive sign convention. Which way should we take positive? Well, in this case, you can see that almost everything is going downwards. So taking down to be positive will be the easiest way to do this question. But for the sake of showing you that it doesn't actually matter which way you take positive, I'm going to take up to be positive for this one. And this is usually something I don't do for a few reasons. One is that I always like to choose the direction of the positive in the same direction as my displacement. So I'm not doing it this time, that's okay. Let's make sure that the question still works when I do this, or that the answer still makes sense. So let's do this. Starting with the velocity. Velocity initially is 0, so I'm going to actually plot that first. And then at the end, velocity is going downwards, meaning that it's opposite to my positive. Because it's moving downwards, it's going to be negative. So I'm going to end up somewhere here at stage 2. I'm going to connect them using a nice straight line. And my acceleration, therefore, would also be negative because the slope of that line is negative. This is kind of straight line. It's kind of, okay, I'll fix my axis there so it looks a little bit better. And good, so I got those down. And in terms of my position, assuming that this is the reference point, then I'm moving in the negative direction. So with my reference point, everything that's above it is going to be positive, everything below it is going to be negative, so I have to plot it in the negative regions. So later on it's going to be, my graph is going to be, or my position is going to be somewhere in the negative region here, pretty far away. And how do I draw my lines or the curve? Should it be this way or should it be this way? Well, I have to look at the velocity. Velocity at the beginning is 0. That means the tangent here, the slope of tangent is 0. And at the very end here, the velocity is a negative value, meaning the tangent here should also be a negative value. So it will look something like this. I will connect these. So 0 velocity, negative velocity, connected using a nice curve, and it looks like a beautiful artwork. Now for our assumptions, we're going to make an assumption that there is no air resistance or wind effects and constant acceleration. You can also add, no, in this case, it's free falling. That means no other forces are acting on it. But in this case, this and this kind of go hand in hand. So you can either include one of them, and that's completely fine. So when it's free falling, it means no other forces are acting on it. And in this case, when it's dropping, there's no air particle pushing it back because there's no air resistance, or wind pushing it in this case, again, because there's no air resistance or wind effect. Okay, let's do part D. We have to use an appropriate equation. So we are going to look for the right one. So information that we have, we got initial velocity, we got the change in time, and we got the acceleration from 1 to 2. I'll label that 1 to 2. And what we're trying to find is the height, which has to do with the displacement. So what we don't have is the final velocity. We're going to go and you look at an equation that doesn't have final velocity in it. This one does. This one doesn't. This is the one. Very similar to the last question, I guess. So this is a good example of how to just do the same question but take the opposite direction to be positive. Last time you had to find the time, this time you have to find the height, but kind of like similar diagrams. I'm going to highlight this equation first because that's what we're using, and then I'm going to write it down. So the displacement from 1 to 2 is going to equal to the initial velocity multiplied by the change in time plus 1/2 of the acceleration multiplied by the change in time squared. And this is acceleration from 1 to 2, change in time from 1 to 2. And let's do this. So the displacement is what we're trying to find, so I'm going to put that in, is going to equal to the velocity 1, in this case the speed in the beginning is 0, and 0 multiplied by any number is 0, so that kind of gets rid of that term right away. It makes my job a lot easier. You got 1/2. In terms of our acceleration, we notice that the acceleration is going down. Our positive direction is up. They're opposite, so I'm going to use a negative value here. And my change in time between the two is 3.41 seconds. I don't have to worry about direction with that. And let's plug it in. I get displacement is equal to negative 57.0358, and the number continues. So then I would have to round it, and I have to figure out the number of significant figures. Here I have 3. Here I have infinite. Here I have 3. So combining everything together, my least number of significant figures is 3. So that will amount to negative 57.0. This is my displacement. Unit is meters and direction is upwards because I always go based on my positive sign convention. Does it make sense in terms of direction? Well, up is positive. If my displacement is negative, that means the displacement from 1 to 2 is actually opposite of up, which is down. And that is correct. My rock in this case is falling from stage 1 to 2, and it's actually falling downwards and not upwards. So this makes sense. But the question here is asking us to determine the depth of the well and not really the displacement. So the depth is equal to 57.0 meters and approximately, and I'm going to box that in. In terms of my assumptions, if they didn't exist, in terms of, and I'll just do no air resistance, I already talked about acceleration in the last question. They're actually very similar. If there is air resistance, then leaving this to fall at the same amount of time, there's going to be air particles hitting it and slowing it down as it drops, and therefore the height that we calculate is going to actually be less than the actual depth. So that's something to keep into consideration. If it took 3.4 seconds and if it was slowing down, that might mean that the actual depth might be something bigger than what we actually calculated. So if we wanted to do this experiment well, we need to make sure that our object is not experiencing much air resistance, and therefore we need to try to pick an object which has a shape which is not kind of like a square, so that air can go around it. Something that's heavier will actually help in this case. So we need to make sure we minimize our errors if we are going to do this as an experiment, if we were to do it. And that's kind of like the evaluation for this one. Let's do our last question now. In this question, we got Mr. S throws a ball up in the air at a speed of 4 meters per second. Determine the velocity of the ball when it returns to his hands. Okay, looks easy enough. Got Mr. Shateri throws the ball up. The ball goes up and it comes down. And imagine that this is kind of going up in the same line. I've just drawn it a little bit with a little bit of movement to kind of exaggerate and show that it's coming back. But in reality, imagine it just goes up, comes down straight. Okay, what do we care about here? Do we care about it going up? Do we even care about this section? Well, first we care about the initial stage when it's going up. Then we determine the velocity of the ball when it returns to the hand, which is right here. So we don't really care about anything that's happening in between. All we care about is our initial stage. So I'm going to actually erase Mr. Shateri for a second just to make this a little bit easier to draw with. So here, we got our stage 1 and we got our stage 2. Our stage 1, the ball is going up. It's going to have an initial velocity of 4 meters per second in the upward direction that's given to us in the question. And it's going to go up, it's going to come down, and at stage 2, the ball is going in this direction and it's going to have a certain velocity. We don't know. We know that through this whole time the object is going to experience an acceleration going downwards. That's 9.81, and it's going to experience this between stages 1 to 2. And there's going to also take certain amount of time is going to take for the ball to fall. So that's going to be the time between 1 to 2. And finally, what else do we have here? The displacement. So what is the displacement from 1 to 2? Well, it starts here, ends here vertically. So if this is my reference point, it comes back to the reference point, so the displacement from 1 to 2 is going to equal to 0. Excellent. We got all the information that we need. I'm going to take down to be positive on this one, and I'm going to use fundamental units of meters and seconds, and I'll highlight those in. Make sure you always have that in your questions. You need to always indicate which direction you're taking to be positive. And I have all the information that I need. So I have initial velocity, final velocity, displacement, position, time, and I have 1 value, 2 values, 3 values. So I can find everything else. This was stage A. Let's do stage B of the question, which is our diagrams. So we got position time, velocity time, acceleration time. And for our position, what's happening to our position? So we start here at the reference points at stage 1, and at the end, we also end at our reference point. So we know that much about our positions. For our velocity, velocity initially is upwards, which is opposite to our positive sign convention, because positive sign convention is downwards. This is opposite. That means it starts at a negative. So I'll put a negative here. And as it goes up, the speed of it is going to slow down, because you can see the direction of velocity and acceleration are opposite. So that means the object will slow down. As it slows down, it will reach a velocity of 0. So somewhere in the middle, it's going to reach a velocity of 0. And then once it reaches 0, it will start falling back, and now the direction of velocity and the acceleration are in the same direction, meaning the object is speeding up. And as it speeds up, it will move in the, it's speeding up in the positive direction now. So our final velocity is going to end somewhere here, and I'm going to draw that using a nice straight line. Like that. And good. Acceleration wise, acceleration is positive throughout the whole situation, 1 to 2. Label those. And this makes sense because the acceleration is in the same direction as our positive, so it needs to be in the positive direction. And our position here, initially my position is, the velocity is negative. That means the slope here should be negative. Draw that in like this. Velocity right at the end here, no, sorry, right at the middle is 0, so that means there needs to be a little tangent going horizontally, because that's a 0 slope tangent. And at the end here, velocity is positive, so positive slope of a tangent here, so draw that in. Connect the lines, going down, going like this, going like this, and I'm going to draw a curve connecting them. Try not to draw hairline things, try to one, or you can do that as a guideline and then fix it with a nice beautiful curve. And this is it. So this is my position time, velocity time, and acceleration time for this situation. In terms of my assumptions, no air resistance or wind effects, and constant acceleration throughout. Okay, good. Part D is going to be using mathematical representation, and let's see what informations we have. We have the displacement, we have the final initial velocity, we have the acceleration, and what we want to find is the final velocity. What we don't have is time, so I'm going to look at the equations. This one has time, this one doesn't, so I'm going to use this equation, highlight it like this. And in this equation, the final velocity for me is stage 2. squared is going to equal to initial velocity, for me it's 1 squared, plus 2 times the acceleration from stage 1 to 2 multiplied by the displacement from 1 to 2. Good. My final velocity in this case is what I'm trying to find. So v2 squared is equal to v1. In this case, that's, let's see the direction. It's going upwards, so my positive is downwards, so they're opposite. I have to use -4 squared plus, and I get 2. The acceleration is downwards, positive is downwards, so that's 9.81. Same direction. And the displacement, for me, the displacement has no direction, and it's actually 0, so I'm just going to put 0 in here. Could have done that in the first step and canceled this whole term out, but that's okay. Do this, I'm going to get v2 squared is equal to 16, and v2 is equal to plus or minus square root of 16, which is equal to plus or minus 4. Now direction does matter, so in this case, I know that when it goes up and comes down, it's going to be going in that direction. This direction and this direction match, and since they match, I have to use the positive one here. So v2 is equal to 4, and in terms of my units, meters per second, and in this case, down is my positive sign convention, so I'll use that. In this case, again, in picking positive or negative, you do have to kind of use the idea that, okay, when it comes down, for sure it's going down, so I have to use the positive down for my final answer. And I'm going to highlight this, and that's going to be my final answer. Actually, almost. I am not going to highlight it because I made a small boo-boo and I forgot to include I forgot to do rounding to my answer. So I have 2 significant figures here, 3 significant figures here. The displacement when it reaches Mr. Shatteri's hand for sure is going to be 0, infinite number of significant figures. So my least is 2. So my final answer is only good to 2 significant figures. So that's meters per second acting downwards, and that is my final answer here. Assumptions, let's assume that there was air resistance. What would have happened? Well, as the ball is going up, air particles will be pushing it, so it's not going to reach as much of a height as it would if there was no air resistance. And then it's going to drop back, and it's not going to be dropping at the same height as it did before, so it's not going to reach as high of a speed here. And also, as it's coming down, air particles are also going to slow it down. So when it reaches here, it's definitely not going to be going as fast. So velocity 2 that we calculated here would be a smaller value, closer to, not closer to 0, but maybe 3 point something, depending on how much air resistance there is and what the air density is like. The effects of altitude on this one is actually pretty interesting, because if imagine if acceleration was being reduced as it went up and there was still no air particles slowing it down, it still reach a certain height, and it would still accelerate the exact same way as it did upwards, downwards, so the velocity wouldn't actually change if it wasn't constant acceleration due to altitude. So this is an interesting question again, but in terms of in this one, let's focus on the air resistance, and if there is air resistance, what would happen? Definitely slower when it gets to this point. I hope these set of questions are helpful in giving you some ideas about how to solve or how to use the 5 equations of motion in vertical situations.